This is the last part of section 3. So after this we'll have covered over a quarter of the course, although some of them here may have been familiar to you so far. In this section it will be a bit novel in the sense that I want to analyse Euclid's algorithm, and the title Consolidation reflects the fact that I'm going to draw together a number of topics which we've seen so far, namely logarithms, recurrence relations, in particular the Fibonacci numbers, and relate all that to Euclid's algorithm. So the problem I'm interested in here is understanding how to estimate the number of steps which we need to carry out to find the greatest common divisor of two integers a and b using Euclid's algorithm. So let a and b be integers. B will always be strictly positive because the idea is we want to divide a by b. Remember, Euclid's algorithm proceeds by first of all dividing a by b, getting a remainder, and then you replace a by b and b by its remainder, and you keep going with this division algorithm until the remainder becomes 0. So there will be a number of steps involved in doing that, and I want to define s of ab, s which is a function of ab. S will be a positive integer, and it represents the number of steps or the number of lines I need in order to get down to a remainder of 0. So the idea is the first line will write a as a quotient times b plus a first remainder, and then we'll keep going, and eventually we'll have a 0 remainder. If Rn is the first remainder that's 0, then n, s of AB is equal to n. Okay, now I can explain this better with some examples. So here's the first example, which corresponds to the one I did before, probably a year ago now. If we take the two integers 33 and 93 in that order, and we try and compute their greatest common divisor, we'll actually need 5 steps to do that if we do it methodically with Euclid's algorithm. Of course, it's pretty obvious the answer is 3, because 33 is 3 times 11, 11 is prime, and 3 divides 93, so the answer is 3. But if we do it rigorously with Euclid's algorithm, we need 5 steps. And there's a slight twist here, because I think last time it's always normal to take the biggest number first, 93. So you'd start with a is equal to 93 and b is 33. But it doesn't really matter if you reverse them, because if you reverse them, the first step is going to involve starting with, in this case, 33. And then we try and divide that by 93. Well, of course, 93 doesn't go into 33, so we have to take the quotient to be 0 times 93, and then the remainder is, of course, 33. And then Euclid's algorithm tells you, well, you take this number down, and you then take this number, and you try and divide that by the remainder. And, of course, this time we're back to what we did before. This is equal to twice. 93 is equal to twice times 33, and the remainder is 27. And then you keep going, the next remainder will be 6, and then we get a remainder of 3, and finally we get a remainder of 0, as in fact we did before. So that's the procedure, and it shows that in this case s is equal to 5, because we need 5 steps. First remainder, second, third, fourth, fifth. Fifth is 0. If I'd have taken s of 93, 33 in that order, then I'd have needed 4 steps, because I could have forgotten about the first line. Okay, that's one example, but a more interesting set of examples comes from the Fibonacci numbers, and that's the point really of today's talk. So if we look at the Fibonacci numbers, of course, the recurrence relation you can see there for the Fibonacci numbers. Capital Fn, remember, is the nth Fibonacci number. At the same time, what this scheme is showing you is the computation of the greatest common divisor of fn plus 2 and fn plus 1. Because if I take A to be fn plus 2 and B to be fn plus 1, then you see I have to divide A by B. Well, fn plus 1 will only go once because the difference is fn, which is smaller than fn plus 1. So the quotient is going to be 1 and the remainder is going to be fn by the recurrence relation. And then you bring the fn plus 1 down, and the next line will write fn plus 1 as fn plus the remainder, which has to be fn minus 1. And so each line will introduce a lower Fibonacci number until you get right down to the bottom. So I need to remind you what these Fibonacci numbers are. So f5, remember, is always equal to 5. The fifth Fibonacci number is 5. The fourth Fibonacci number is 3. The third Fibonacci number is 2. And the second Fibonacci number is 1. So you'll get down to 2 is equal to twice times 1, and the remainder is 0. So here's the remainder 0, so that's when we stop. And how many remainders do we have on the right-hand side? Well, we've got n remainders. We started with fn minus 1, and we're down to 0, which is number 1. In this, I'm just counting the list of remainders, 1, 2, 3, up to n. So that tells you that the number of steps needed to compute this greatest common divisor is actually n. So S is equal to n. I'll write that down in a moment, but first of all, I really should record the other fact that we've also shown. This also proves that the greatest common divisor of any two Fibonacci numbers, I started in this case with any two adjacent Fibonacci numbers. Here I started with fn plus 2, fn plus 1. That greatest common divisor, what is it equal to? Well, it's equal to this number, which is 1. So, in fact, this scheme also proves that any two adjacent Fibonacci numbers are co-prime. Their greatest common divisor is equal to 1. And the number of steps needed to arrive at that greatest common divisor is n. Okay, and that's what I'm interested in today, the number of steps. So the number of steps is n. That's what this proposition, so again, this is taken from the notes, the lecture notes. This proposition in the lecture notes in its first part says that the number of steps needed to compute the greatest common divisor of fn plus 2 and fn plus 1 is equal to n. Two adjacent Fibonacci numbers. Okay, that's the first statement. Now there's a sort of converse to this statement, which is of perhaps greater importance. And that's the second part of this proposition. And let me read it out first, and then I'll try and make sense of it. So for simplicity here, I'm going to suppose that A is positive and greater than B, greater than 0. And suppose we need n steps to compute the greatest common divisor of A and B. In those circumstances, I can assert that A has to be at least as big as the Fibonacci number fn plus 2, and B has to be at least as big as fn plus 1. Before, in the first bit, we were saying that if we take A to equal that Fibonacci number and B the same, equal to the other Fibonacci number, then we do need n steps. This is saying more. To sort of understand the significance of this, you see, take n to be, say, 100. Suppose we need 100 steps to execute Euclid's algorithm to get a remainder of 0. That's quite a lot of steps, at least if you're doing it by hand. What the proposition is telling you is that if you need 100 steps, the numbers you started with are bigger or equal to these Fibonacci numbers. In particular, they're both bigger than the nth Fibonacci number. Okay, so if you need 100 steps, the numbers you started with are both bigger than the 100th Fibonacci number. And that's pretty big, that 100th Fibonacci number, because the Fibonacci numbers grow exponentially with n. The formula for the nth Fibonacci number, which I'll give you soon, remind you of soon, is exponential in the sense that it involves some constant to the power of n. So to get 100 steps, we actually have to have started with much larger numbers than that. And that's sort of reflecting the efficiency of Euclid's algorithm. If the numbers are smaller, we don't need 100 steps. That's what it's saying. Okay, let me now prove this proposition because it's a good exercise in induction. So let's embark on the proof. And the first thing to remark is that this statement, the statement of the proposition, is trivial or immediately true if n is equal to 1. Because you see, the point is this: A has to be, if you look at this hypothesis here, B has to be at least 1 and A has to be at least 2. So A has to be at least 2 and B has to be at least 1. But if you take n to be 1, the third Fibonacci number is 2 and the second Fibonacci number is 1. So that means these equalities in the box are satisfied when n is equal to 1, trivially. So we've certainly got the induction going. Now let's look at a general step. So what I want to do now, as usual, is to assume that this result here is true. We want to prove this result literally as it's written for this value of n. But let's suppose that the same result is true when n is replaced by n minus 1. Okay, so let's suppose that this proposition is true for n minus 1. We have a given value of n, maybe we're trying to prove it for n is 100, and let's suppose it's true for n for any numbers when n is 99. Okay, so the point is this, that now we want to prove this for the number of steps equal to n, say 100. And if we assume that, what is the first step in applying Euclid's algorithm? The first step is to divide A by B. Okay, and then the next step is to take the B downstairs and divide it by R, so that the second line here will be A is equal to some other quotient, let's just call it Q primed, times R, plus another remainder, which I call R2. And then we keep going. This is a 2. But you see, the point is, if we need n steps to compute the greatest common divisor of A and B, then to compute the greatest common divisor of B and R, we only need n minus 1 steps, because it's everything that's left. We don't need the first line anymore. So if S of AB is equal to n, we can assert that S of BR is equal to n minus 1. So now we can apply our hypothesis, our inductive hypothesis, because we have two numbers for which the number of steps is n minus 1. So that will tell us, the numbers are no longer called A and B, they're called B and R, but that will tell us that B has to be at least as big as, not n plus 2 now, but n plus f of n plus 1, because n has been replaced by n minus 1, and R has to be at least as big as fn. Okay, that's what our inductive hypothesis will tell us. Okay, so let me clean that up and retype it. That's our conclusion. So this is what I've just said here. B is at least as big as fn plus 1 and R is at least as big as fn. Now, what have we got to do? We've still got to finish this off. So we've still got to, we're assuming that, but now we've already shown that B has to be at least fn plus 1. So that is that statement. So we've already got that. We need to prove this inequality for A. Okay, well, A, let's think what A is. A is equal to, it's written here, QB plus R, but Q has to be at least 1, okay, because A is bigger than B. So when we divide A by B, it will go at least once. B is strictly positive. So A will be at least as big as 1 times B plus R. And I'm going to change the page now, but you see that's going to be at least as big as B plus R. B plus R is Fn plus 1 plus Fn. That's Fn plus 2, which is exactly what we want. So I meant to have changed the page before. So this is what I'm saying, that A is at least as big as 1 times B plus R, but we've already shown this box here. So B is at least Fn plus 1, R is at least Fn, but the recurrence relation for Fibonacci numbers will tell us that Fn plus 1 plus Fn is equal to Fn plus 2, and that's exactly, that gives us this statement. Okay, so we've got that statement as well. We already had this statement from here. Okay, so that finishes the proof of the second proposition. So I think that's the sort of proof, you know, I would expect you to be able to follow. Okay, so now let me try and use that fact to deduce a result about the efficiency of Euclid's algorithm. So let's just look at it again. The proposition is telling us that if we need n steps to compute the greatest common divisor of A and B, then in particular, I'm more concerned about B actually, in particular B has to be at least as big as the Fibonacci number Fn plus 1. So in other words, B has to be big, that's the idea. If we already need n steps to execute Euclid's algorithm, B has to be big, has to be at least as big as the n plus first Fibonacci number. Okay, and that will now lead us to the following theorem. That will enable me to prove the following theorem on this page, and then I'll stop. So again, let's suppose that A is bigger than B, positive, strictly bigger than B, bigger than 0, and we're trying to apply Euclid's algorithm to find the greatest common divisor of A and B, the first step being to divide A by B. Suppose it takes n steps. Well, suppose it takes S of AB steps, that's my notation. S of AB is the number of steps which it's going to take, and I'm going to call that n in a moment. Then the point is that this function S of AB is big O of the logarithm of B. Okay. Now what does that mean? It means that the number of steps divided by log B is bounded. Okay, in other words, the number of steps is sort of comparable to the log of B, which is much smaller than B. That's the idea. Doesn't matter what logs I'm using, but LG means log to base 2. We normally use log to base in this course. If you change the base of the logarithms, you only change the log by a constant, an overall constant, so that won't affect this big O. So remember, big O for functions or sequences, as we have here, simply means that the function on the left, thinking of this really as a function of B, but A is an even bigger number, so it will also be true that this is big O of log A. S of AB divided by log B, log to base 2 of B, I've chosen, is bounded. And we're thinking of B as getting bigger, so this is bounded as B goes to infinity. That's what this, that's a bit off the page, that's what this theorem is telling us. Okay, let me now prove that. And to prove this, I just need the formula for the nth Fibonacci number. So remember, as I said before, the proposition we've just proved tells us that B has to be at least as big as the n plus first Fibonacci number. Now, that is, of course, bigger, typically bigger than the nth Fibonacci number, and the formula for the nth Fibonacci number is 1 over root 5, phi to the n minus psi to the n, where phi and psi are these roots here, because remember the Fibonacci number the recurrence relation for the Fibonacci number involves the quadratic equation x squared minus x minus 1 is equal to 0. The associated quadratic is x squared minus x minus 1. That just comes from the recurrence relation, just by the way we normally solve the recurrence relation. So that means that the general solution would be a constant. You take the two roots, and the two roots are a half, well, 1 plus root 5, 1 plus or minus root 5 over 2. So you need to take some constant times the first root to the power n plus a different constant times the second root to the power n, which is what I've done here. And then the constants are determined by the initial conditions. For example, that the f0 is 0 and f1 is 1. So phi here is this root with a positive sign. That's the golden ratio, of course, and psi is the root with a minus sign of this polynomial. So that's the nth Fibonacci number. Now, if n is odd, psi, don't forget, psi is a negative number. Psi is negative. So if n is odd, minus psi to the n will be a positive number. So this expression fn will be greater than 1 over root 5 phi to the n. Okay, let me record that. So let me say it like this. So here I've multiplied both sides by root 5. So I'm now looking at root 5b, but I'm really interested in fn root 5 times fn plus 1. And I've just said that that's going to be at least as big as phi to the n. That's if n is odd. If n is odd. But if n is even, I could actually use the formula for fn plus 1, in which I have the powers here fn plus 1. So in that case, this would actually be greater than or equal to phi to the n plus 1. So in either case, this is going to be true. If this is true, this is going to be true as well. So in all cases, fn plus 1 times root 5 is, or let me say it like this, fn plus 1 is greater than or equal to 1 over root 5 times phi to the n. So root 5b is greater than or equal to phi to the n. Okay, now I've almost finished. Now I take logs of both sides. Log of a product is the sum of the logs. So log of root 5 is a half log of 5. It doesn't really matter. It's just a constant. Plus log of b is greater than or equal to, when you take log of an exponent, the exponent comes down. So it's greater than or equal to n times log phi. Log phi is another constant. So if you divide both sides by log b, you see that as b goes to infinity, I think there should be a b here. If b goes to infinity, really, any constant over log b, that goes to 0. And what we discover is that n divided by log b is bounded. Okay, is bounded by some constant, which we could even estimate, but I'm not going to bother. So n over log b, but n is s of ab, so that gives the theorem. That's what big O means. N over log b is bounded as b gets larger. Okay, and what that is telling us is that Euclid's algorithm sort of works. The number of operations, the number of steps is going to be really, it's going to relate closely to the time it takes the computer to execute Euclid's algorithm. So really what we're saying is that Euclid's algorithm will execute in log time. That makes it very efficient. It's like the algorithm we had for taking powers, taking an integer to the exponent of another integer, which I showed you a way of doing that, which really only the number of multiplications you need depends on the log of the exponent. Here we've got a similar result here for Euclid's algorithm. And that means it will execute very quickly when you ask the computer to work out the greatest common divisor of very large numbers. It does it very quickly. And so I'll finish with one example of that, in fact my favourite example of that, if you ask Euclid's algorithm to work out the greatest common divisor of 100 factorial plus 1 and 100 to the power 100 minus 1, I think the greatest common divisor is 101 actually. But in any case, it does that in only, of course these numbers are huge, but it does that in only 337 steps. Okay, and it's an illustration of the usefulness, the power really of Euclid's algorithm. Okay, I'll stop there. In fourth week, we'll be starting the sort of big chunk of graph theory, which starting with definitions and so forth.